Hello, my name is Russell Jackson, and I will be presenting on behalf of Dr. Moore and Dr. Yanakomsu the role of cementitious liners on the structural preservation of overburdened buried concrete pipes. I want to thank you in advance for your interest and would love to answer any questions in the upcoming question sessions. Here's a brief overview of what I will be discussing in this presentation. I will begin by providing a brief introduction to cementitious liners and concrete pipes. Then I will outline some of the objectives we are hoping to accomplish in this research project. I will continue by explaining how loading and bending moment are characterized in buried concrete pipes, and how the corresponding load resistance mechanisms are described in our design model. I'll explain how numerical models were used to evaluate the design model, followed by our results, conclusions, and the future work we hope to accomplish as a continuation of the research presented here. Concrete pipes are designed to resist earth and surface loads such that unreinforced concrete structures do not crack, and reinforced concrete structures have limited crack widths. Crack widths are limited to protect the pipe walls from stormwater infiltration and consequently corrosive and abrasive damage. The bending moment resulting from earth and surface loads is widely regarded as the critical load mechanism in rigid pipes, which includes the reinforced and unreinforced pipes under analysis in this study. These bending moments are most severe at the crown, or the top of the pipe circumference. An image showing relevant locations around a pipe circumference is provided in the top right corner of this slide for reference. The bending resistance of the crown wall is subject to deterioration resulting from corrosion, abrasion, and also increased loading due to unprecedented earth and surface loads after the initial pipe burial. This research project focuses on the need to rehabilitate intact pipes which have not undergone deterioration but have been subjected to increased loading after pipe burial. Pipes are commonly rehabilitated with trenchless solutions as excavation-based methods of repair lead to increased financial and social costs. One such trenchless solution is the application of cementitious liners. Cementitious liners are centrifugally cast with a spinning head that travels along the interior of the pipe. Cementitious liners may also be applied by hand. The liner is applied to the interior of the pipe wall and left to cure until the admixture reaches an adequate tensile strength. Proper curing of the liner may require rerouting of stormwater prior to application. An image of a cementitious liner being cast with a spinning head is shown in the bottom right corner of this slide. Although the pipe in this image is corrugated steel, not concrete, the image still shows how cementitious liners are applied. So there were 4 research objectives we were hoping to achieve in this project. The first was to investigate the potential need to rehabilitate intact pipes subjected to increased earth loads after pipe burial. More specifically, we were looking to examine how additional load would result in unsafe levels of cracking in intact pipes, and how cementitious liners could be used to return the cracking capacity of the pipe to safe levels to prevent future deterioration. In this study, we look at 2 different cementitious liners, a sprayed liner with a cracking stress of 11.3 megapascals, and a cementitious mortar with a cracking stress of 7 megapascals. Our second objective was to identify failure modes for the repaired systems. As noted in previous slides, bending moment is the critical failure mechanism in rigid pipes, where peak bending occurs at the crown. The bending moment induces compressive stresses towards the pipe exterior at the crown and tensile stresses towards the pipe interior, which may result in cracking. That said, we are looking to determine whether cracking due to bending occurs in the liner or the concrete pipe first. This is explained in more detail in the coming slides. Identifying failure modes for cracking brings us to the third objective, which was to create a design model that can be used to select the liner mortar thickness required to restore the pipe to a sufficient bending moment capacity to prevent cracking. Finally, the results of the design models were evaluated with numerical models. Concrete sewer pipes are typically buried at depths greater than 5 meters, meaning the effects of surface live loading can be ignored. Instead, design was based around earth loading from the surrounding soil. The bending moment at the pipe crown resulting from soil load can be approximated using the Hogue solution. Then Moore's simplification to the Hogue solution can be exercised, which sets the equation equal to the rigid pipe limit, which is appropriate for the concrete pipes under analysis in this study. The bending moment from the simplified Hogue solution is the loading used in the design model. The design model was created such that cracking is prevented in both the liner and the concrete pipe. An image of the liner cracking in tension can be seen in the first image on the left, and cracking in the concrete pipe can be observed in the image on the right. Preventing cracking in the concrete beneath the liner, as shown in the second image on the right, ensures that large stress concentrations do not form as a result of the discontinuity caused by the fracture. Large stress concentrations would cause further cracking in the liner, leaving the pipe susceptible to deterioration. Noting that cracking must be avoided in the liner and concrete pipe, the resistance of the crown wall was computed by assuming perfect bond between the liner and the host pipe. This assumption results in a linear strain profile over the composite section. This strain profile was evaluated with force equilibrium and moment equilibrium, where peak strains in the linear strain profile were set to half of the tensile cracking limits of both the liner and the concrete pipe, resulting in a material safety factor equal to 2. The design model is solved iteratively with different liner thicknesses until the system avoids cracking strains in both the liner and the concrete. Numerical models were created to evaluate the results of the design model. The soil pipe system was discretized into two-dimensional plane strain solid elements, as shown in the images above. Perfect bond was modeled between the pipe and the liner. The maximum tensile stresses observed in the numerical models were compared to those computed in the design model. Before I present the results from the design models and numerical models, I thought it would be useful to outline some of the elements on the plot where the results will be shown. On the y-axis, we have strain, and then on the x-axis, we have the distance through the composite section, meaning both the liner and the concrete pipe. The left end of the plot is the liner region of the composite section, as shown by the label and arrows. Moving to the right, we pass through the concrete pipe until we reach the exterior of the crown wall on the right end of the plot. The cracking strain of concrete and the liner are also labeled on the plot, recalling that these strains should not be exceeded in order to avoid cracking. The zero strain line, which will show the location of the neutral axis of the composite section, is also provided. The dashed blue line shows the strain profile obtained from the design model. The line is perfectly linear, as linear strain was an underlying assumption in creating the design approach. The strain distribution intersects with the cracking strain of concrete, but falls below the cracking strain of the liner. This shows that the design of the liner repaired system is governed by the cracking strain of the concrete pipe, rather than the liner. This is a result of using a liner with a cracking stress of 11.3 megapascals, which is almost 3 times greater than the cracking strain of the concrete pipe. Now the same plot is provided with the results from the numerical analysis, which is shown with the red line. The red line appears mostly linear, and the maximum difference between the strain profiles was observed to be only 0.000025 strain. The plot presented in this slide shows the strain profile for the mortar repaired pipe. It can be observed that the strain profile intersects with the cracking strain of the mortar over the mortar portion of the plot, but the concrete pipe portion of the composite system does not reach its respective cracking strain. This indicates that the design of the 7 megapascal mortar is governed by the cracking strength of the mortar rather than the concrete pipe. This is a result of using a liner material with a cracking strength closer to that of the concrete pipe in comparison to the cementitious liner shown previously. Once again, the strain path from the numerical model is shown in red. The maximum difference between the lines is 0.000025 strain. An analytical solution for estimating the required liner thickness to prevent cracking in intact concrete pipes was developed and evaluated against numerical models. The numerical models indicated that the design model produces conservative estimates of liner thickness. The differences between the design and numerical models results from the assumption of perfect pipe rigidity in the design model, which results in conservative estimates of earth loading. Two liner materials were considered in the analytical solution: a cementitious liner with a tensile strength of 11.3 megapascals and a cementitious mortar with a tensile strength of 7 megapascals. The design of the liner was governed by the cracking strain of the concrete pipe, and the design of the mortar was governed by the tensile strength of the mortar. The failure mechanism critical to the liner design appears to rely on how the tensile strength of the liner material compares to the tensile strength of the host pipe. If the liner has a much higher tensile strength, then the cracking strain of the concrete pipe governs design. As the tensile strength of the concrete pipe approaches the tensile strength of the liner, the cracking strain of the liner governs design. In this research project, a design approach was created for rehabilitating intact concrete pipes subjected to unprecedented earth loads. In future iterations of this research, the authors hope to create design methods for a range of pipe deterioration states, including pipes which have experienced cracking, loss of cover, and loss of reinforcing steel. This is the end of the presentation, and I want to thank you for your attention and for your interest. I hope to see